Welcome to BioBabes,
the Sanctuary of Science,
the biome of biomimicry,
the arena of alchemy,
where we're talking to the brightest minds who are reshaping our future.
And today we're talking with Dr. Christina Maher, who is enhancing human communication with neurotechnology.
Welcome, Christina.
What got you into neuroscience and doing your PhD in this space?
Well, thanks for having me, first of all. I love this setup. Yeah, I mean, I've thought about this a lot over the years, you know, going back to, this was probably 8 years ago. I think it was two main sort of catalysts. I think we all have these events in life that kind of push you to do something that you wouldn't have considered in the past. And so the first thing was losing my dad. I was in my early 20s. He passed away. He got really sick. He passed away really suddenly. So it was like alive on the Thursday, gone on the Saturday. 5 kids. I'm the eldest of 5. And to me at that time, I couldn't understand why the hospitals couldn't keep him alive. Like I knew that we had, these devices or this sort of like the technology that we have in hospitals. And at the time I thought, why don't we have a way of doing these tests earlier? Because I felt that he had probably been sick for a longer time than what we knew, but the symptoms only started to show right at the end when he actually ended up going to the hospital. So that was the first thing, and growing up where I grew up, we lived in a relatively low socioeconomic area, so it left my entire family in this, financial disarray. But then it happened again. 4 years later with my son, he also got sick. Doctors sent him home, and they said he had the flu. But then when we went to like a third doctor, they said you have to take him to the hospital straight away, because if you don't, he's gonna die. So this sort of second event really showed me that we just don't have the technology that we need to detect disease earlier, and again to detect it before symptoms are showing. Because with my son, by the time we took him to the hospital, the surgeon that operated on him said that if we didn't bring him in at that exact moment, we would have lost him. And when you think about that, that's just crazy, right?
That's wild.
So these two things, I think for me, I was like, what is going on here? My family, my parents were not educated, so there wasn't like anyone we could talk to. There wasn't anyone we could ask for support when the illnesses were happening. So for me, I was like, I don't know anything about this industry. It was so foreign to me, and there was no health education. And I think, even my dad, before he passed away, he was quite unhealthy. He wasn't eating right, he was drinking a lot of alcohol, and I think that if he had had access to a lot more of this information, like he didn't grow up in this era of social media where you can probably find out that most of these types of things are not good for you. So I was like, I need to know about this whole industry. I became the breadwinner for my family, so I was working full time. I was a single mom, and so I was like, I can't
While
go do
doing your PhD?
Well, not yet.
Okay.
So I was like, I can't go do a degree. I can't go do a medical degree to become a doctor. But I wanted to know how this worked. So I was like, I'll do this neuroscience degree.
Wow.
And I've always been obsessed with the brain. I'd always been obsessed with how we think and, why people behave the way they do.
Yeah.
So I was like, I'll do this degree. It was like mostly online. So I would work in the day and study at night. And then from there, I was also working in tech, so I was doing software engineering. And during my degree, I discovered brain-computer interfaces. And actually, the first one I discovered was Synchron's, like one of their early papers. And I was like, oh my God, like this makes so much sense. This is the perfect combination of tech and neuroscience. And I became obsessed, and then I did a stint in the clinic, and I did a lot more imaging of the brain, and I got really obsessed with the tech side. So then, I basically pivoted to do a PhD in biomedical engineering, focusing on the neural engineering side of things. And I won a scholarship. It worked out really well. I assembled this awesome team. It was super supportive. One was like head of neurology at the hospital, because I think for me, for the PhD, given my personal journey and my experiences, I wanted to do something that would have direct impact on people, because I had worked with patients. I wanted to work with patients during my PhD. I didn't want to just produce something that was just going to sit on a shelf somewhere. So I really kind of wanted to do something that addressed some of the most severe brain conditions. Because, I have a giant family on my mom and my dad's side, and I've seen almost like the entire spectrum of brain conditions. There's been a lot of mental health issues. I have a cousin with a child who has cerebral palsy. I have another relative who has epilepsy. I have an uncle who had a brain tumor. So all of these things I'd seen, growing up and up until that point. So I really wanted to make sure that I did something that was meaningful and impactful.
Yeah, that's amazing. Just so I can get this right, you worked in finance and then worked as a software engineer and then did your PhD in biomedical engineering and now are in neuroscience.
Yeah.
And you've just brought this all together. That is wild, just background-wise.
Yeah.
Do you see your work more as healing the brain, extending it, or revealing abilities that humans already have?
I love that question. I think all three. So you said healing the brain, extending it, or revealing. Yeah, no, absolutely all three. I think, in the space of healing the brain, there are just, you both know, an absolute gamut of conditions that people suffer from across the lifespan. In my work, what I really want to do is help people improve their cognitive ability and cognitive capacity and their ability to communicate with others. And so, I guess it applies to anyone, whether or not they are already able to communicate or that they don't have some sort of impairment, right across to people who are speech impaired. I would say, that's the main focus of my work.
And you were talking a lot about brain-computer interfaces and how you got into that. And I know there are a lot of myths out there around brain health, around what BCIs can achieve, also between implants and wearables. So can you walk us a little bit through what can BCIs do today?
Yeah, so I think it's helpful to look at how BCIs work. And I'll try and keep it brief. Basically, you get two types of brain-computer interfaces. You get implantable ones and non-implantable ones. So the implantable ones obviously go inside your head. They are invasive. They require surgery. They require a balance of a number of variables or parameters, the safety, how long they can last in your brain, the power consumption, the sending of data, because it's stuck in there, right? You're not going to take it out. And to put it in, you need to, you need to, go past the blood-brain barrier, which is actually why Synchron's device caught my eye, because they don't do that. They go up through the chest and they go into a blood vessel.
Whoa.
So they don't open your skull at all. There's no open.
So it's very, very small. It's like microscopic. It goes through a vein?
Yeah.
Wow, okay.
Yeah. And it was actually modeled on the stents that they use in the heart to open up blood vessels in the heart. So the implantable ones are far more risky to get, and so the only people who are going to get that are people who really need them, people with really severe conditions. On the other side, the wearables, these ones you can take on and off. So you can put it anywhere that you can get a good signal, and really those ones can, again, apply across the range of conditions, whether it's really severe brain conditions. So, we do use electrodes that are just outside the head that sit on the scalp to diagnose things like epilepsy. But then you can also use them for, I saw recently a group from MIT released a paper that is using an AI-enhanced wearable to help people with learning. Wow. So, you've got that spectrum there of what the devices can do, and it really just depends on what application you want to use it for.
Yeah, and talk to me a little bit more about these different kinds of wearables. You said you put it anywhere you can get a good signal. What does that mean? Does it need to be on my forehead? Does it need to be, like on my neck? Like, what does that look like?
Yeah, so I like to think about devices in terms of their application. So, for example, if you're using a device to treat ADHD, one of the recent groups I've seen is using a stimulation device. That's got to go here. What you're looking at with these devices in terms of where you place them, whether it's an implant or a wearable, is where in the brain you're placing it based on what function or what you want to pick up, what signal you want to pick up. So for motor movements, Synchron's device is sitting in the motor cortex.
Wow.
So, if you want to move your finger or control a virtual finger, you're going to imagine moving the finger, so you want it in the part of the brain that's doing that task or that activity.
That's cool.
Whereas for going back to the ADHD example, you use a lot of your prefrontal cortex to do things like planning. It's involved in, I guess, what we call executive function, a lot of cognitive tasks that we do at work. So in that case, you want the device somewhere here. And for something like ADHD, I think it's not severe enough to get an implant. So wearables work well, and they can give you real-time feedback now with some of these deep learning models and with advances in hardware. They can basically measure the activity in real time and give you real-time feedback. So you have this closed loop of information that, like, while you're working, it's like my brain's getting tired, I want to modulate what's happening, or maybe I want to stop and have a rest. So I forgot your question.
So just different kinds of them, and you brought some with you as well. This is great because exactly, like, I'm curious how and where you wear them. Can you show us a little bit more of, like, the different examples? Because in my mind, I'm envisioning like this giant helmet, like Brian Johnson's helmet he's been wearing for like the psilocybin trials.
Yeah, so that one's really interesting because what he's done there is, okay, so this is the other thing. You can think of listening to activity in the brain as like, the analogy we always use is like listening to a bunch of people in a stadium. If you want to find your friend in the stadium who's talking to your other friend, you are probably not going to hear their conversation. You're just going to hear the roar of the stadium,
Noise.
right?
Yeah.
But if you want to find your friend, you might need more microphones, and you might want to place them in certain positions. So in terms of listening to the brain, because so devices do one of two things. They're either passive or active. So the passive ones are just listening, recording, observing the signals, and doing what we call readout, so reading out the signals. Whereas the active ones are actually producing a response in reaction to what's happening in the brain. And you have two types of active ones. You've got proactive ones where they predict something that might happen. So some of the deep brain stimulation devices that are used for epilepsy, for inhibiting seizures, these ones will predict if a seizure is going to happen, and they send an electrical pulse to inhibit that seizure activity.
So it's like a not just one-way connection. It's not just listening for your friend's microphone. It's then yelling back at them and being like,
yeah, exactly. It's doing something based on, again, that particular application and based on the particular condition that you're trying to either treat or modulate. And then there's the reactive one. So like the neuro wearable will be reacting to what it's reading in real time. So going back to that microphone example, what we look at when we look at the brain is basically the state of your brain. We call them brain states. So if you want to particularly treat a specific disorder, that means your brain is either in that state all the time or it's transient. And so something like if you have a brain tumor growing in your brain, that's going to be in your brain all the time. Or if you have seizures, that's transient. It's going to come and go, and you don't know when. And so what we can do now with wearables, and something like Brian Johnson's one, which I'll get to in a second, is with the wearables we mostly look at brain states. And so if you think about it like this, if you have, let's say in the oceans, big ocean of water, if you have a wave starting 500 meters out at sea, you're not going to see the wave. The water's going to look very calm. But as it gets closer to shore, it changes shape, it changes size, velocity, speed, all that sort of stuff. By the time it crashes, it looks different, but it still started over here. So it's still a reflection of what's happening over here. So what we can do with wearables is we can get, I guess, a snapshot of what's happening in your brain overall, like your brain state. So For something like epilepsy, we want, you know, a really detailed picture.
Yeah.
We want to know where that's happening. And they actually do that with epilepsy when they diagnose it, is they can get a sense of where the seizure starts. And this is important if you want to go for surgery and things like that. Whereas if you just want to measure tiredness, like, oh, this person's feeling tired, you don't need that level of detail. You can just get an overall picture. And so, yeah, with Brian Johnson's device, what they're doing is they use a technique called, is it NIRS? Yeah, they use near-infrared spectroscopy. The way NIRS works is it shines light into the brain. The more light sensors you can get on the head, the better, because you can get a better sense of the overall activity. So that's why he's got the helmet. I can't remember how many sensors, but I think it's how many light diodes they have, but I feel like it's like in the 3,000 range from memory, but I could be wrong. Shine the light in, blood absorbs it. So the idea is that, and MRI machines work in a similar way, functional MRI machines work in a similar way, where they are looking at wherever there's a lot of neuronal activity, there's going to be a lot more blood flow. So the idea is that the blood absorbs the light, and then the sensors read that back out. And so however the light changes between when it was sent in to how it was read out, and there's so many algorithms for this, that will give you an indication of what's happening. So what he's doing is, with his devices, they're pharmaceutical companies, I'm pretty sure, are using this to understand how drugs and different types of, I guess, pharmaceuticals work in the brain in real time. So you would have seen his mushroom experiment recently. There exactly is the perfect example. You put it on, he takes the mushrooms, and you can measure in real time and across the entire time a longitudinal measurement of exactly what this drug is doing in the brain. I will say that NIRS and you know, some of these techniques don't measure directly the brain activity. They're measuring what we call a proxy of brain activity. So it's sort of a secondary measurement, whereas something like EEG, which is MySpace electroencephalography, this is measuring exactly the electrical activity, the exact voltages caused by the neuron activity. But it still gives a really good picture. And I think, from memory, his device was multimodal. So there's this big sort of movement towards combining different modalities, and modalities are just like different methods of measuring what's happening in the brain. From memory, I thought his one was EEG and NIRS, which is near-infrared, but it might have changed. And then I think what's unique about their one is, like, they have some unique algorithms for processing the signal that is being read out. But yeah, his one's really interesting, and I think this is one of the biggest benefits of the wearable devices, is that we're going to be able to get so much more detailed picture of how people are responding to drugs. And then we'll be able to titrate dosages in real time, or just make them more personalized and more, I guess, suited to that person's need, rather than just going in with the blanket dose, which is kind of what is currently done now.
Interesting. So there's so much, it's still developing, still happening.
And I'm also very curious about brain-to-brain communication, using these devices to actually have a clear idea what's happening in one brain, and sending that information into another brain, and maybe even causing an action, emotion. Wouldn't that be equivalent to synthetic telepathy, artificial telepathy, or something like that? How does that work, and what does the future look in that sense?
Yeah, this is one of the most exciting spaces, and it's, I guess, the space I'm in, and it's the idea that if we all were wearing a device, I'm wearing one right now, I can show you in a moment, we wouldn't even need to speak. We could just communicate with our thoughts. And so I guess, you know, if we take a step back.
Wait. Okay,
So,
let's just repeat this again.
Wait.
You're saying we could communicate without speaking to each other.
Without saying
We're
a
just
word.
like mind-to-mind connection.
Yeah,
Okay.
exactly. Through a device still, okay, but you can imagine the power of that.
How, in what language, or in what form, in what format does that data come into your mind?
This is exactly what people are working on right now. And the idea is that we can read out signals from the brain. So I can put a device on you, I can know what you're thinking. But as I said before, looking at brain states, it's a very coarse signal, or what we call a crude signal. It's very high level, it's not detailed enough. So if I say the word dog and you think of the word dog, we might be thinking of different things, and we don't have specific markers for words just yet. But
Interesting.
well, not in wearables, but in the implant space, there's been some really interesting work recently where they are starting to, I guess, decode the signals and decode the meaning of signals, and they've done it in MRI. So in functional MRI, this is where they're measuring, again, blood flow in the brain, but they've also done it with implants. And the way this works is essentially you have a model that you read out the brain activity whilst the person is either thinking of words or watching a movie. Well, there's two parts.
So crazy.
You're either looking at something, so looking at an image, it could be a movie, it could be a picture, or you're thinking of words you want to say. The model reads out the activity happening in your brain. Again, different ways of reading that activity. It can be blood flow absorption, it can be electrical activity. Then the model is linking the activity in the brain to what you saw. We call these like encoders and decoders. I'm not going to go into the detail of those. And then, it essentially links the activity that was happening in your brain at that exact time to the time you saw it. We look at where it was happening in the brain. So there's a whole lot of basis behind why we think that particular activity means a certain word or a certain, or means, I guess, the gist of what you were looking at. And that's what they've shown. They've shown this, I mean, there was a Nature paper, I think last year, that showed 3 participants in an MRI watching movies, and then the people in the movies were talking, and then from those people's brain activity in the MRI, they were able to capture the gist or the semantics of what that person was watching.
Wow.
Yes.
So I just want to repeat this back to you, just so that I make sure I understand it. So because we have like at least a basic understanding of what parts of the brain light up when someone is sad or happy. So then it records those signals while someone is watching the movie, and then if it's at a sad part, you can understand, oh, something sad is happening. And then if it gets happy, so you can kind of understand like what's going on that person is experiencing without you seeing that movie. Is that right?
Yeah, exactly.
Wow.
Exactly.
Okay.
And I mean, I guess the thing is, right now, if I look at someone's brainwaves without them watching that movie, if they already felt sad in some way, we could pick up some crude markers for that. But what the field is trying to get to is word level detail. And the reason that's so complicated is because words have different meaning to everyone. And this is why I think this research is so important, because the idea that we communicate in words is actually not a very great way of communicating.
It's crazy, because I think many people underestimate how limited language can be.
Yes, exactly.
I think it's the ultimate, most advanced technology, and it is a great technology, language, but even in different languages, you can say different things. There are different words in certain languages that don't exist in others.
Yes.
And what if there is so much more than that? What if even if you combine all languages in the world, you're not going to achieve that level of accuracy or limitless communication that you could achieve? What you guys are working on.
Yeah, absolutely. And you know, this is my big vision for the future. It's this idea that, so right now we communicate in words. It's a terribly, I guess, well, we'll call it a low bit rate. It's a very slow way of communication, right?
Communication is low bit in
low. You have this massive dimension of activity in the brain, from single neuron activity to clusters to networks, and they're all involved in thought, processing your thoughts, communicating. On top of that, your brain's doing a bunch of other things. You know, our brains are all multitasking right now. Your brain is holding you up in that chair. It's holding your eyes open. It's allowing you to listen to what I'm saying.
Keeping the sun out of my eyes.
Yeah. It's stopping you from like yelling out, you know, inappropriate things. Like it's doing so many things.
Yeah.
And then on top of that, it's processing words. So the dimension of space, of activity, of what's happening, down to then when you say, you know, my name, Christina, or whatever, it just condenses and also removes out a ton of information. And there's so much research where it's like, is my color red, your color red, or you seeing what I'm seeing? And so I just believe that, when you go to someone's house and they serve you a plate of food. So I think food is a universal language, right?
Food?
Food, yeah.
I like that.
Taste, do you mean like
some sharing a meal together is a universal language of
communion,
of caring, of it's a sign of friendship. It's a
basic need
it's
too.
like
Everybody understands.
Everybody understands it, and
Yeah.
so there's other universal languages. I think math.
she says like sex,
like sex,
But is
Okay,
sex
math,
a universal language?
I feel like
procreation, maybe.
people,
Okay. Yeah, maybe
but I'm just thinking about
You brought it up.
memes that are like
maybe the act of it, but I don't know if
it's like instinct. It's
people's
like an instinct.
understanding of it, maybe not.
Yeah.
Yeah.
No, but it is, and that's the thing, like there are these universal languages, maths is one, numbers is one, code is universal language, but not everyone understands those.
Yeah.
So I just think that if we can communicate at the level of neural activity, which is essentially electrical activity, we could achieve just a much better alignment, human alignment, in so many facets of life. Like think about when you've ever had a misunderstanding or miscommunication with a loved one, or a misunderstanding at work. This used to happen a lot, particularly when I was in software engineering, where it's like, you tell someone what to do and they're like nodding and they're like yes, and you think you understand each other, and they go away and they build something completely different.
Yeah.
I've gotten
Words
that
are
a lot.
insufficient.
Yeah.
We need more than just words to communicate.
Exactly. And then you can also go to these other examples where it's like, my son's getting older now. He says less. I still want to know what's on his mind. You know what I mean? Like,
There's so much more, and I think certain people without wearables get to develop some sort of sixth sense or intuition around that. It's interesting that it has a name in science, and that we're really going into that way.
I mean, we just talked about some of the applications of neurotech. I have heard and read a little bit about Meta and their mind reading. So what do you know about Meta's mind reading project?
yeah, okay. So
I love the excitement already.
yeah, so this was really exciting for two reasons. Well, actually for many reasons, but there's a lot of groups working in this space, but their experiment was particularly elegant because of the way they designed it. So the first thing is, I just bumped my microphone. Do you think that's okay?
You're okay.
Okay.
You're sweating. We're all
It's
sweating.
all right.
We're doing great.
Yeah. No. Okay, so yes, Meta. First of all, the technique they used was not looking at electrical activity, they're looking at electromagnetic activity. So they use something called magnetoencephalography, which is looking at the magnetic field around your head. So we've all got a magnetic field around our head at the moment.
Okay.
And this method of measuring brain activity is far more accurate than some of the other techniques, because you can go down to like a millimeter level precision in the temporal function. So temporal means time, so it's like across time. You can get the level of precision that you want to measure the brain activity. You want it to be as close as possible to the time of the neuron firing or the time of the neuronal cluster activity. And you want to be able to capture that really fast. So again, like looking at that sort of bit rate. And I can't remember the specific difference at the moment. You guys are going to have to fill this in. But I should know this. But so the reason MEG is advantageous is because of that.
MEG is the
temporal
magnetoencephaly.
Yeah, magnetoencephalography.
Okay, magneto.
So anything with like encephalography just means the brain. So we have electroencephalography, that's the electrical. So these machines at the moment are giant, and the reason they need to be giant is because they need to keep them really cool. They need to keep them at below sub-zero temperatures.
Definitely not the temperature we're at right now.
Definitely not the temperature we're at right now. And they also need to put them as close as possible to your head. So this device is called a squid machine. It stands for like super, I always forget this, super quantum interference device. Supercomputing quantum interference device, something like that.
Love it.
Which I don't know why they use the word squid, but maybe it just sounds cool. Because it looks like a squid, so it looks like it's got the things coming out. That's right. And actually now they've got a wearable version of this. And there's different methods of doing it. Anyway, the reason it was elegant is because they would show the participant the words on the screen and then give the person time to remember it. Then the person would type it out. Now, what happens in the brain when you're reading something is that you're doing multiple processes. So remember I said we're doing multitasking all the time. A lot of the existing experiments, the person would be thinking and watching and viewing at the same time as they're recording. So you're not getting this cleaner sort of differentiation between the actual generation of the words in your brain. You're mixing it with the visual perception and everything else that's going on.
Wow.
So that was one thing I thought was nice about the design of their experiment. It's like not super interesting details, just like if you're a scientist, you're like, what did they do? And yeah, they basically showed incredibly high accuracy of the brain being able, of their decoder models being able to decode the MEG activity while the person was typing these sentences. Now, the reason this is cool is because, MEG devices are giant at the moment. No one's going to walk around with that on their head. But in the future, these devices will get smaller. Everything's getting smaller. The EEG devices are getting smaller. MEG's going to get smaller. We now have these ultrasounds getting smaller. You would have seen these handheld ultrasound devices, like portable, wireless, all that. And so if MEG can get smaller, it becomes a really nice complementary data point to the other data points we have. And so that's one of the reasons they're using that. They did it in EEG as well, actually. They did both in this particular study. But I think the interest was in MEG because MEG has got that advantage in terms of its data capture rate.
What do you think it's the goal behind Meta's mind reading project? And how does that compare to other things?
They're already reading our mind, right? Like Mark Zuckerberg's already reading and controlling our mind anyways.
Because this is not openly shared on, this is not something that people are usually talking about in the media. This is not on the news. There's no people just following what's going on. But Meta is trying to really expand.
Yeah, I always like to think of new tech in terms of the tech we already have. So you're right, social media, when we look at it, they use all these algorithms to see where on your phone you're looking. They create heat maps. I created this in my last startup where it's like you track the person's eyes. They know what you're going to click on. They know what you stare at for longer. There's already so many algorithms that are essentially reading our minds by reading our behavior. But that does require you to have an overt behavior. We call an overt behavior is an observable behavior. So anything that's still in your mind that you haven't revealed, something that's covert, is something they're never going to have access to. But most people in the general population aren't very good at concealing what they think or what they feel. And in particular, when it comes to things like social media, the way they design it is to get a reaction from you. As you know, all this clickbait, rage bait stuff, it's designed to get a reaction. So most people will not be good at concealing their true reaction. So I guess the idea of this kind of mind reading tech is that you don't need to even go to this level. That's one thing I think that they'll be able to just capture exactly at the moment it occurs. But the other thing is, are we going to have phones in the future? What are we going to be using? What are we going to be looking at? If we don't have these devices to act as a stimulus, act as a stimuli to incite or induce a response, you're still going to want to know what someone's thinking or about to do or about to say. So in that case,
are going well. It's
exactly.
If you had a choice, and you have a choice with the phone, you can put it away. But the Meta glasses, once they're in,
and they're reading faces too, right? I like what you just said, which is right now we're already they're already reading our minds to reading our behavior.
Yeah.
And like the more data points they get, the better. And this next iteration is just even more data, and it's to a deeper level, like biologically. It's in your brain.
Yeah, yeah.
That's awesome.
And you know, when I think about this, there are so many, I guess, I don't like the word ethical because it's just so, it can be subjective, but really there's a lot of issues around, this is something I'm looking at in my work, is how do we define where your brain actually starts and stops, and where the model starts and stops? So all of this tech uses deep learning models, uses maths, uses algorithms, and you know, you have to think about who's designing this.
Yeah.
Who's deciding that, you know, this particular voltage of activity means this, right? Or who's designing the experiments? And so, you know, this is something we're looking at in the field. There's a thing I'm looking at now, which is how do we know that someone was intending to do what the device says they were intending to do?
Oh, interesting.
Because we don't have great markers of intention when it comes to non-motor movements. So if I'm about to move my finger to click on a cursor, there's plenty of research around that sort of 0 to 500 milliseconds before I move my hand. You know, like if you go to grab your cup of tea,
Yeah.
you don't tell your brain to go, you don't tell your hand to go grab that cup of tea. It just does it.
You think
You
about
just
it,
want
yeah.
to, I want to drink my tea, your hand is going there.
Interesting.
You know?
Yeah.
Actually, people that have bionic limbs, they have to relearn how to think because they have to tell the limb to go and grab
sense.
the cup.
Wow.
yeah.
So, Christina, we've been talking a lot about the brain states and decisions and how we're reading minds. What about free will? Is free will real?
I've thought about this a lot. Particularly when you start looking into the consciousness space, it's like, especially that subconscious space, it's like your brain is doing so many things you're not aware of. I'm so not an expert in this space, and I'm so not the best person. There's so many better people to talk about this. You know, Sam Harris has got some great work on this. Robert Sapolsky talks about it. I think for me, looking across the spectrum of research that explores free will, I lean slightly towards the idea that we don't have free will, because if you think about it, and if you look at two things, people who have diseases, people who have conditions like seizures, or they can't will away their seizures, right?
Yeah.
The brain's doing its own thing.
Yeah.
Then you look at people who commit the worst crimes. Another example. There's been so many studies that show these people have abnormalities or anomalies in the structural, the anatomy of their brain, in the function of their brain.
Wow.
You know, we know so many things are immoral, and yet people still do these things. And there's been so much research on that too. And then taking it back to basics, something more relatable, you know, how many times have you just had this belief, and even if you're presented information that contradicts that, we still cling to things we want to believe, even though we have the actual evidence presented to us that it might be wrong.
Yeah.
So
Interesting.
personally, you know, it's such a contended space in the
Yeah.
field, but I sort of lean slightly more towards the idea that perhaps we don't. That perhaps we don't have free will.
I remember we had a conversation around being fearless and well, we're at this stage in our careers where we're just like going hard on everything. We're just building startups, just like taking a lot of risks. What have you learned about consciousness that allows you to be much more fearless?
Yeah, I don't know if it's just the consciousness space, and it might be a whole constellation of experiences across life, but this certainly has given, I guess, a scientific basis to it. And for me, it's the idea that looking at the research in epigenetics, this idea that everything your ancestors went through, your great-grandparents, your grandparents, your parents, is passed down through the genome to you. And so the way we respond to situations, to environments, to everyday life is, I guess, modulated by whatever they went through in their lives. And there's so much research on this. The idea that all of their past experiences, good and bad, live in your genome and live in this subconscious space of your mind. And so tying that into everyday life, and the idea that your brain is doing its own thing before you are aware of it. It's preparing your thoughts before you're aware of them. I just get the sense that everything that we fear about, doing new things, trying things that we might think are hard or difficult, comes from this subconscious space. And if you can tap into that at the time that it's happening, or before it happens, and change your response so that it's, so that
you're breaking the cycle.
Exactly. It's like you're doing something different. You're moving away from what you're almost like genetically programmed to do, what you're subconsciously programmed to do.
Wow.
And if you think about it in that way, and you're consciously aware of it, when you go to do things like, being a founder is incredibly hard. You're always being challenged by your ideas. But if you have this vision and you're able to stick to it, and you're able to realize, like, you just say to yourself, like, what am I actually afraid of? I tie that in with a lot of things I've done over the course of life where it's maybe gone terribly, and you know what, nothing bad really happened. I'm still alive, everyone's still here, we're all fine.
Yeah.
And you think back and you're like, why was I worried about that? So for me, there's that bit. And then there's also like the whole quantum dimension side of things, where I just think, maybe there are multiple dimensions that we don't know about yet. There's so much cool research happening in that space. And I think, in the future, we're going to find out. Someone's going to find out what exactly it is that's happening, and whether our brains actually are acting on their own, or, we talked about interbrain synchrony, with like your monthly cycle. We think that women, when they all live in the same house, they synchronize.
Yeah.
I think that happens with brains too.
Oh, I love that.
Oh,
yeah.
So it's like more like a brain. It's like a
psychological cycle syncing.
It's almost at yes. Like it's almost at, in the way it happens now, I think is very behavioral. Where they say, the 6 people you surround yourself with is who you are.
Oh, interesting. Yeah.
There's got to be like a much more scientific neural activity level basis to that. And of course, when you surround yourself with amazing people and they're doing amazing things, and you also watch their behaviors and all that, you absorb that. And that's all very visual.
Yeah.
But there could be this whole electromagnetic side of it too that we just can't see and we don't know about yet.
I just got chills. Like, this
you know what I mean?
Yeah, like I feel smarter. This is why we do this podcast, is to feel smarter talking to people like you. But then, like, if we're surrounding ourselves by this, then
Yeah.
You have mentioned that you are wearing a device this whole time.
Yeah.
Can you show
Where
us
is
that?
it?
And then some of the devices you've got as well.
So, okay, first of all, the one I'm wearing. No, let's start with the big one.
Okay.
So this is to see the difference, right?
Yeah.
So this is a 5-channel wearable. You can see it has the sensors here. You would normally put some saline gel on them, and that's to get a better contact with the skull. And so you'll put this on like this. This is going to be interesting.
Cool.
Oh no, and then the other device I'm wearing is actually in the exact same spot, which it shouldn't be. But
it looks like a crown. It's so stylish.
I love it. It looks like a spider.
do I look
like
like
hugging.
a queen from the Middle Ages?
You look like a futuristic queen,
Oh,
actually.
like we just put some trinkets on, some charms on it.
Your neurotech,
wearable.
your neurotech, it doubles as a Halloween
I need to see
costume.
this. Oh, this would actually
I love
such
this.
a
It could be on a fashion catwalk. Like, I think wearables are going to start being more part of like fashion culture.
Oh my god, I love that. A wearable fashion show?
Or like actual crowns.
Oh,
A
yeah.
wearable
That would
fashion
be
show,
so
because there's
cool.
jewelry and like this looks like a
Yes.
beautiful crown, and you can
yes.
actually match it and make.
We can just do that here. This is a great catwalk.
Oh, yes. Also, they're getting smaller.
I just had this crazy thought about what if ancient crowns, like from ancient, even before monarchies existed, were actually devices?
Were they devices?
Why would they?
whoa.
Why would they?
like,
Like, what if they were all wearables? What if there was technology back in the past?
Wait.
And actually crowns from like wearable technology.
Yeah, and we wouldn't know because we didn't live in that time.
Yeah.
Yeah.
Can you
And
see-
also the materials of the crown was like gold.
Highly-
Yeah. Highly conductive
conductive
materials.
Conductive.
Oh my gosh.
And they were all exactly.
Yes. Oh my god.
And they
Do you
all
think there's
had like,
something
and like
that we have
also
not?
the stones. Okay, if electromagnetic, if there's, you know, the heart has an electromagnetic field, the brain
Yeah.
has an electromagnetic field, and you place it in one of
Yeah.
the most important
Yeah.
electromagnetic fields. With the stones, and stones, I mean, to extent, without getting woo into this, there is a science behind the magnetic, the energy.
Absolutely.
And it's positioned in a way
Absolutely.
that is almost doing what this is doing, but instead of reading, it is transmitting energy straight from the stones into the novel's head.
And imagine if the stones were absorbing the energy of the moon. You know how when this is very woo-woo, but like I did go through a phase where I'd like put the crystals.
Me
and,
too.
you know, you put
We've
them
all
on-
had our crystal phase.
Okay, we've all had a crystal phase. Okay,
I think
good.
any
We
nerdy
all had
girl
a phase with the moon and everything.
You know, this is definitely before I did my degree, but yes, I still have those. I just think they look pretty, to be honest.
Yeah.
If this was gold,
We can
they
definitely
should make this in,
No,
I'll
we
make
can,
it in gold.
I wear this like 3 times a week or something, and if anyone asks you, well, I'm just scanning my brain. I'm just
No,
checking
we'll
my
just be
neuro-
like, what do you mean? I'm not wearing anything. Or just psych them out. What are you talking about? There's nothing on my head. No, but I want to show you these as well, because the devices are getting smaller. Obviously, this is okay, but my hair is going to be interrupting the signal. It's going to be very noisy.
So do we get better signals from bald people?
No. Do you know
No?
that's a myth?
Really? Okay,
Yeah.
this is a good myth.
People
Okay.
think this.
Okay,
Why is
wait.
that a
So
myth?
so it's a myth
Okay,
that we get better
I can't
signals
remember
from.
specifically, but when I worked in neurofeedback, what you do is you scratch the skull a bit to take off the dead skin on top, and then you put the gel. It's like a conductive gel, and then you put the electrode cup on, right?
So it's like cleaning your scalp.
You have to clean their scalp.
Okay.
Yes. Yeah, I did that.
Well,
You do it with something, and then you use alcohol, and then you scratch it a bit to create a bit of a rough surface. And this is why this method is not great, because
you're scratching people's heads all day.
yeah, and so people with sensory disorders, like
Yeah.
people on the spectrum or anything like that, and especially kids, they don't like it. So it's not a perfect technique, right? It's not a perfect treatment. But yeah, so that is putting stuff on the head. You want to be directly on the head. These, on the other hand, this is broken. I broke it trying to put it on, which means I couldn't put it on very easily. But
Bad user interface. Yeah, I could use
yes.
some work.
Actually, we can turn it now.
Can you hold it up in front of your white shirt like that?
Yeah,
I
so
think that's your camera.
Yeah, right over there.
okay.
Perfect. That's
So these are earphone sensors. You can play music through them, do anything you would normally do, take calls. But they have 2 sensors here, and they have, I think, 1 inside here somewhere, or maybe not, I can't remember. And so yeah, I think it's like a 4-channel, because you got 2. And you can wear these all day long. So, but the only caveat with these then is that they're only measuring from like your temporal lobe activity. Now, so remembering how I said before, you want to put things in the areas of the brain that you want to know where the activity is coming from. With this sort of stuff, it's like, yes, it's kind of only getting the activity here, mostly, but you remember my example of the ocean, there's still a bunch of activity happening that is going to create sort of like throw-off signals around the rest of the head.
Yeah.
Ripple effect,
Ripple.
exactly. So I think earbuds are going to take off. I think anything around the ear, and the reason that around the ear is nice, I'm going to show you this one too, is that you've got this patch of skin where there's no hair. So you can get a really nice, clean fit. The only thing with those, they don't fit everyone's ear properly. Everyone's ear is super unique.
Probably made for men.
Potentially, yeah.
In general.
Yeah. But yeah, I've seen a few companies this year announce big raises for like either a behind the ear patch or an earbud. Yeah.
Like the one you're wearing?
Yeah, so the one I'm wearing, do you
wearing
want me to
one-
take this off for a sec so I can show you the one I'm wearing? Okay, so the one I'm wearing, and I don't know if you're going to see it very well on the camera,
I did not even know that was there.
is about as small as it
so cool.
gets now. Actually, I'm going to take it off so I can show it to you how small it is. This is an Australian company. They're doing some cool stuff too. And the companies that have announced raises this year are actually smaller than this. If I can get this off without absolutely annihilating this device. Okay, so it's essentially got 2 sensor, 2 channels. It's called 2 channels, and then it's got what we call a ground or a reference, because when you measure brain activity, you're always measuring the activity between 2 points.
Okay. So it's like sending a signal and then responding.
Yeah, you always have to have what we call a ground or a reference point, which is why some of these devices with way more sensors are able to pick up so much more activity. All of these devices pick up both the activity you want to know about, but then they also pick up a ton of noise. Anything outside the head, you have to think about, like, between the brain and the skin on the outside, there's about 7 layers. So the electrical activity going from inside to outside is always going to be impeded by those layers. So by the time it's measured on the scalp, it's the tiniest voltage of electrical activity. So the more of it that you can pick up, the more likely, the idea is that the more likely you are to find what you're looking for, if you're looking for biomarkers of things, because you're going to pick up a lot of noise, but then you remove that with what we call signal processing techniques. We remove the noise. But now what they're starting to show is, you know, you might have 2 sensors here, and then you might do studies with the whole head thing, but then you just correlate what's happening here with what you're picking up here, and then over time you don't need this. So, you know, in the future, I think we are going, if more people wear these wearables, we're going to start collecting much more data.
Yeah.
And you can produce these now at really low cost. They're so much easier to produce than, say, 10 years ago. So it's like these wearables we have on our wrist and so on. Once we start collecting more data, we're going to have so much more data to work with to better understand what's going on in the brain. We're going to have it across longitudinal time frames. So right now, all the long-term data we have from like a year, more than a year of data, is all from people, mostly from people, like 99% from people with brain diseases or disorders or conditions. So like epilepsy or motor neuron disease.
So we don't have like...
So you don't have healthy brain data for long periods of time. So the idea is that over time we want to get more healthy brain data, because otherwise you're making these models that do all these things, but they apply to someone whose brain operates differently.
Oh, it's true. And now there are more products also around. Well, there are also wearables that are treating people, and you don't need to have a very extreme disease, but more like period cramps.
That's right.
So
yes.
What's happening in the space in terms of wearables, just treating more like daily life situations?
Exactly. This is something I'm actually super excited about, is this idea of bioelectroceutical therapy or bioelectroceuticals, which is using electrical therapy
instead of pharmaceuticals.
I
love that.
Pharmaceuticals.
It's called bioelectrical. Can we look this up? It's electroceuticals, not bio. I added in the bio. Some people add in the bio, but it's electroceuticals. Delivering electrical impulses to specific nerves, organs, or tissues to regulate their function.
Like electrostimulation.
Yes.
Okay.
Yeah.
So I have one of those. I have a electrostim pad that I put on my stomach
like the
for when I
TENS.
have cramps.
Yes.
Yeah, for TENS.
Yes.
Yeah. And then there's the new one you'd mentioned, like the headband. I think it's Sapphire Neuroscience. That one's super cool. That is coming out as well. Are there other companies that you're really excited about, or like, I think you mentioned some women entrepreneurs in the space like yourself?
Yeah. So Sapphire is really interesting. Their clinical trial research that's coming out now is, their results are looking really good. So Sapphire's device is a headband. You wear it, I think, in the week before your period, and it modulates the pain receptors. It acts on the pain region of your brain by sending in a what they call a closed loop stimulation. It's a certain type. There's many types, as you mentioned. There's the TENS device. There's something called TDCS, which is transcranial direct current stimulation. I think that's what they use, but they might use TACS, which is another kind. Don't quote me on that. But yeah, so you use it for 20 minutes, I think. I think in the days leading up to your period, not when you have your period. And yeah, the results that are coming out now from some of their clinical trials are really cool.
Can I ask a couple pop culture quiz questions?
Yeah, what are the pop culture quiz questions?
So I recently binged Pluribus, this new show by the same director of Breaking Bad and Better Call Saul. And it gave me the question, where's the line between treating depression and robotic happiness?
Ooh. I mean, is there a line? Does everything need to be a line?
I think that's a good,
Yeah, this came to mind too for me when I watched Black Mirror.
I'm so glad you mentioned it. Yep.
Yeah, the Common People episode. Oh my God, I loved it because it was potentially a little bit silly, but at the same time, you can see how this would work. So you can see someone who has some sort of brain abnormality or abnormal function, whether it's from an accident or whatever, like it was in the show. Yeah. Then you're like, oh my God, we can give you this device and it can return you to your normal self. So when I think about people and I think what they showed was semi-realistic in terms of the parts of the brain they were showing that they were going to modulate once they gave the device to her and how she was going to feel. I think all this sort of idea of real-time ads coming out of your brain, that requires a lot of power, it requires a lot of data transmission, all these sorts of things, like even using the Wi-Fi to connect. There was this scene where they like are out of the Wi-Fi zone or something.
Yeah.
These sorts of things still need to be resolved, but when I think about people who suffer from these mental illnesses or mental conditions, if your life, if these conditions are chronic and your life is so impaired and it impacts your ability to function in everyday life, of course you're going to want this device. And so for me, everything's about, like I said before, I'm very individualization and personalization pilled. I think everything has to be assessed by the user. Yeah. And if you want to have robotic happiness every day, shouldn't that be your choice? Shouldn't it be your own free will? Yeah. In saying that, the other side is like, are we the right people to make those decisions for people? Of course, I personally believe life is about suffering. I think people benefit from having those highs and lows.
Exactly.
Not extreme highs and lows as in like manic depressive disorder or something like that, but you benefit from experiencing suffering and from experiencing
100%.
pain. But when it's chronic and it's impacting your daily life and those highs and lows are such a roller coaster that you can't get anything done, you can't function, that's where something like this would be of benefit. And I will say, I don't think any of the founders in this space building to treat these conditions are thinking about giving people robotic happiness. Because the journey to create this is so long. Like, these companies have to raise massive amounts of money. They have to go through this massive process of clinical trials to meet like one target outcome. By the time you get there, I don't know, I feel like these founders would be so tired and be like, why would we then go beyond that? Or, if they achieve what they set out to achieve, I just think I can see why it would be possible. But I don't know that I can't see why people would do that. Maybe Sam Altman. I don't know. So yeah, I don't think there's a line, and I don't even know what is robotic happiness. Like, are robots happy?
I think I
don't know.
I agree with you, because I used to think, oh, why would we want to have so much power over people's own feelings or how they want to feel? But people with depression, like, they cannot stand up in the morning and shower. They cannot do so many of the basic things because the condition is really twisting reality to them. And I do see huge help that this can be. And I also think there is a lot of myths behind what the intentions are. It's like, we can develop technology and it can be developed to very good things. It can be developed to very bad things. But most people in science, in medicine, in like people like you are really fighting their life because they want to make a better world.
If you look at, so I've worked with a lot of patients, if you look at how debilitating some of these conditions are, especially things like seizures, I've been in surgery rooms where they've implanted electrodes. So if you don't respond to medication, that means you can't control your seizures. You could die at any moment, right? So like one surgery I watched was they implanted this 14-year-old boy with what we call stereo electrodes, and they do this. It's incredibly high-risk surgery. They're putting 13 sticks into his brain. It's the longest, it's like hours long. And you only do that when you have such a bad condition. And well, they do this process so they can understand exactly what part of the brain is causing the seizures, and then they can cut it out. And if you think about when you cut out a part of the brain, you can't put it back. So you have to get this very correct.
You got to get it right.
Yeah, you've got to get it right.
Yeah.
When you see that level of an impact of a brain disorder or condition on a person's life, you can't even think about some of these like more sinister reasons to do things, you know, because there's so much to solve just in that disease space that you could spend your whole life just solving that first. And you know, I know a lot of people think about how we might use our minds to control drones or to control robots one day. And I think those are really cool applications, but the amount of tech you would need, the amount of data you would need to train, and just the, like, I don't know if we'll get there. I don't know if we'll get there in my lifetime. Maybe we will, maybe we won't. But I think that there's so many other great problems to work on that really good people in the field are working on. I don't think they're gonna like just start shifting over into some of these more peripheral spaces, I guess.
Like, what's one science-backed habit or trick that we should be doing to improve our brain health?
Okay, so I love this question because so many people ask this, and it's like, guess what? There isn't one trick.
Dang it, we wanted this.
There isn't one trick that any one person should do, or there isn't one trick that everyone should do, because everyone responds individually to different things. So I think the one thing people should do is the one thing that works for them, that they can do daily, that they can turn into a habit. So like for me, I do box breathing a lot. But it's taking me time to build up that habit. I don't do a lot of, you know, meditation and stuff as such. Meditation has so much research. It's amazing. I think everyone should try it.
Yeah.
I don't have time to do like 30 minutes of meditation a day. But I do a lot of box breathing. I do a lot of self-talk as well.
Interesting. It's the same as mental health.
Yeah. You know, this idea that you can sort of top down regulate how your brains are, and you know, this kind of conflicts with the whole idea of free will. Okay, but these are some of the arguments that are out there. But yeah, the idea that there's one thing people should do, I don't think so. It's whatever works for you that you know you're going to stick to every day. And I think things that are low cost or no cost, like breathing, like meditation. Oh, and you know, I use music a lot. So, you know, before we recorded this, I listened, you know, for people who respond to music, that's like a great way to enhance something, right? But then there's people that don't respond to music at all. It doesn't make them feel anything. So that's not going to work for them.
So you would say then that brain health is correlated to mental health, basically. Then.
Oh yeah, absolutely. Well, you know, like there's these studies that your social environment or your social experience, particularly as we age, is extremely protective against conditions like Alzheimer's and dementia. So you've got this direct correlation, and there's a lot of work in this space that having a social life, or I guess
like community,
the community, or the opposite, which is not being lonely, and or when they look at people who are lonely and how loneliness contributes to people's mental health and brain health over the lifespan, and particularly in older age. This directly impacts your brain health, and it impacts your mental health. And I mean, like, that seems obvious, but...
It seems, but it's not.
It's not. I'm very introverted myself, but whatever level of community that works for you. You know, they look at these communities where people live in these sort of tight-knit, sort of like closed spaces, like particularly in Japan, you know, the areas where people live the longest in the world.
The blue zones.
In the blue zones.
Those are all directly related to how those people interact and absorb the benefits of being in those communities.
We're asking this question to all of our guests. What excites you the most about the future?
Ooh. If I think about my entire journey to now, what I'm most excited about is highly, highly personalized treatments and prediction and detection of illnesses and disease. Not even just in the brain, but like across the brain body. Being able to detect diseases before we're aware of them, being able to treat them in a personalized way, and in a way that is actually effective without side effects.
Oh my gosh.
Yeah, I think that, you know, if I think about the main biggest benefit that I think we can get from this tech, it will be that. It will be like highly precise, highly accurate prediction, detection, treatment of all diseases.
I love that. And that's perfect full circle with why you got into this in the first place.
Yeah,
which
exactly.
is amazing. I love that. Thank you
you
so much.
for
We really
coming.
appreciate it. Thank you
for having me.
for joining us on BioBabes. We appreciate
so
it.
much fun.